Now comes the second law. The second law is slightly different in the sense that the second law gives you introduces an important quantity, which is the entropy S. Now, historically, the second law was formulated with the beginning of the heat engines, right? And what is a heat engine? You realize a heat engine is basically an engine which takes a certain amount of heat from a hot reservoir, does an amount of work W, and dumps an amount of work QC to the cold reservoir. So this is my hot reservoir and this is my cold reservoir. And clearly, I mean, here if you have designed an engine, then you want to know what is the efficiency of that engine. The efficiency of the engine is defined as QC over QH 1 minus that. This is how you define the efficiency of the engine. So historically, the origin of the second law lies in the development of heat engines. People developed diesel engines and all these things were developed historically, and people wanted to know, well, how do I calculate the efficiency? I mean, they're not validating. I mean, there has to be a method of calculating the efficiency. And therein came in the second law. So once I have a heat engine, you can see that there is a work involved in this. There is also an exchange of heat that is involved over here. And the efficiency of this engine is given by 1 minus QC over QH. Clearly, if I want to apply the conservation of energy, then I have QH is equal to W plus QC. And this machine doesn't seem to violate the conservation of energy, therefore it doesn't violate the first law. So it's in principle allowed. But then I want to know, is there any upper bound of in the efficiency? Can I have a 100% efficient engine? So that is precisely where second law steps in. But on top of it, remember that the second law also introduces the concept of entropy, which is a state function. You also realize that in this particular diagram that we have drawn for the heat engine, there is a flow of heat that has been indicated, that it flows from the hot to the cold. But why is that? Herein also the answer comes from the second law. Now, just for completeness, the opposite, the reverse of a heat engine is a refrigerator. So a refrigerator is essentially a heat engine which is worked in a opposite cycle. So you take an amount of heat QC and you essentially do an amount of work W, and you dump an amount of heat QH to the cold to the hot reservoir. Now, if you recall, if you have seen the old refrigerators at home, then you would have seen that there is a wear mesh that is fixed at the back of the refrigerator. That wear mesh essentially dissipates this QH heat in the environment. So that backside of this is hot. That is why also the external units of air conditioners are very hot. Now, let's just quickly go to the next page. There are two statements of second law. The first statement is essentially a Kelvin statement that tells you that no process is possible whose sole result is the conversion of, this is the complete conversion of heat to work, is to convert heat completely to work. That you do not get. So let us just reformulate this to write down that whose sole purpose is the complete conversion of heat to work. Now this essentially rules out a perfect heat engine. Right? Because this essentially tells you that the efficiency of a heat engine must be less than 1. The alternative statement is Clausius' statement. And that tells you that heat essentially flows from a hot to a cold bottle. In other words, that you cannot have, no process is possible where and let's say whose result is the transfer of heat from cold to hot without doing any external work. And this essentially rules out a perfect refrigerator. Now we want to have the proof of equivalence for this. So let's just come over here, and we want to have the proof of equivalence. Let's just remove this. So what does this mean? What do I mean by proof of equivalence? I want to show that if I violate the Clausius statement, I also simultaneously violate Kelvin's statement. Similarly, if I violate Kelvin's statement, I also simultaneously violate Clausius statement. So suppose now I have an engine which I shall denote with a bar because it violates Clausius statement, and here I have an amount of heat QC that goes in over here, and right. So by definition, by conservation of energy, this is exactly this. So I don't have to worry about anything. Now what can I do? So this machine clearly violates Clausius statement because I can see that the heat has been extracted from the cold reservoir. So this is the hot reservoir and this is the cold reservoir. The heat has been extracted from the cold reservoir and has been dumped into the hot reservoir. So in principle, what I will do here is I will operate another machine which is a regular Karnaugh engine that extracts an amount of heat QH, does an amount of work W, and dumps an amount of work QC to the cold reservoir. Up to this is fine, but remember that this output W is in my hand. So I can clearly regulate this. I regulate it in such a way that it dumps amount of heat Q to the cold reservoir. Therefore, if you look at this whole machine together, what do you get? You get Q. If you look at it carefully, then you will get an amount of heat which is QH minus Q, which is drawn from the hot reservoir, and an amount of W which is converted to work. So this machine clearly violates Kelvin statement. So the first proof of equivalence essentially tells you that if I have a machine that violates Clausius statement, that is equivalent. If you violate Clausius statement, that is equivalent to violating Kelvin statement, right? What about the other way around? The other way around is when you violate Kelvin's statement. So if let's violate Kelvin's statement by purpose. So I have a machine with which I denote by bar because again it's violating a statement. It draws an amount of heat Q from the hot reservoir and does an amount of heat W, completely converting this heat into W. So when you complete, because this then violates Kelvin's statement. Now this work I can use to drive a refrigerator. A refrigerator would take up a heat QC and would dump a heat QH. So this one violates Kelvin's statement. Now let's look at this whole thing together. If I look at this whole thing together, then you realize that I have QH minus Q So I have a machine which essentially is in which there's a flow of heat from the cold reservoir to the hot reservoir without any external work that has been done. So this now violates Clausius' statement, right? So please note that the conservation of energy should give you Q is equal to W and W plus QC is equal to QH, right? So essentially, yeah, so these two should give you. So this violates Clausius' statement. So essentially, if you violate one statement, you violate the other statement, right? So now we want to look at what is an ideal heat engine. And this is like coming back to the question, what is the maximum efficiency I can get? What is the maximum efficiency I can get? Because clearly there is an involvement of heat and work in these machines, right? And the answer lies in what is called a Karnaugh engine. In Karnaugh engines, all the processes that are involved are reversible. Well, a reversible process, you can imagine, they, in analogy with mechanics, they are essentially frictionless processes, which means there is no dissipation process in mechanics. This is the analogy that you have with mechanics, and if you reverse the time, you can reverse the inputs and the outputs in a reversible process. So the equivalent of that in mechanics is a frictionless process. Since essentially there is the reversibility implies an equilibrium, this necessarily means that this process has to be a quasi-static process. All reversible processes are quasi-static process, but the reverse is not generally true. Now, what is a Karnaugh engine? Well, a Karnaugh engine is the one. So I have a Karnaugh engine. It takes up a heat QH and it dumps a heat QC, and essentially in a Karnaugh engine, the taking up of the heat and the dumping of the heat so in a Karnaugh engine, and the dumping of the heat happens at fixed temperatures. So QH is taken up by the system at a temperature TH, and QC is dumped to the cold reservoir at a temperature TC. In all the other processes that may be involved in this Karnaugh engine, there is no heat exchange with either of the reservoirs. So here, a very short note. What is a reservoir? A reservoir is the one which has an infinite heat capacity. And that essentially means even if you take away certain amount of heat or you dump certain amount of heat to the reservoir, its temperature remains fixed. So let's go ahead with this. This happens at TH and this happens at TC. The dumping of the heat happens at TC. So once again, this is my hot reservoir and this is my cold reservoir. Now TH and TC are therefore so isotherms. And herein my zeroth law comes in to rescue me. Zeroth law tells me that how I can pick isotherms, right? But it remains, because the rest of the processes must be adiabatic, I do not know, because no heat exchanges are allowed. So I have to figure out how adiabatic processes would be. Well, if you take the working substance of this engine, to be an ideal gas, then I know for the ideal gas PV is equal to mkBT, right? And the internal energy of the ideal gas is 3 by 2 mkBT. If you're smart, if you want to be, you can take this factor to be more general depending on the type of ideal. So we will consider the ideal gas to be made up of monoatomic particles. So once I have this, then I know that d cut q is equal to du plus pdv. Remember, in the last lecture we discussed this, that the generalized pressure, the force for a hydrostatic system is minus P, and therefore this is what it becomes. Now, since I'm not allowing any heat exchange, it follows d cut q is equal to 0, so du plus pdv must be equal to 0. So du is 3 by 2. Let's just write this over here as PV, 3 by 2, PdV, well, let's be d of PV plus PdV is equal to 0, so 3 by 2 dP plus 3 by 2 PdV plus PdV must be equal to 0. So this means 3 by 2 VdP plus 5 by 2 PdV is equal to 0, and you can clearly see PV to the power gamma is constant. So this is an equation of an adiabat, provided your working substance is an ideal gas. So if I want to look at the PV diagram, then I have the isotherms and I have the adiabats, right? So the isotherms is where the heat is taken, this is TH and this is TC, and the adiabat is, and the second one is where the heat is dumped, the isotherm corresponding to TC. These two are adiabats, and therefore there is no heat exchange that is allowed. So this is the simplest form of a Karnaugh engine. Now Karnaugh's theorem tells you that the following: no engine that operates between two temperatures TH and TC is more efficient than a Karnaugh engine. Remember, what is so special about a Karnaugh engine? Because all my processes are reversible. Number one, the efficiency of the engine does not depend on the working substance. So you might as well do it with a magnetic substance instead of working with the ideal gas. Essentially what you will have is the same efficiency if your temperatures TH and TC remain the same. So once I have that, so let's see if I can prove it. So what I will do over here is I will take a non-Karnaugh engine, which means which is standard in the sense it extracts an amount of QH amount of heat, dumps a QC amount of heat, and does a work W. This is your hot and this is your cold, and that work is used to run a refrigerator which extracts an amount of heat Q prime and dumps an amount of heat Q prime H to the hot reservoir. If I now look at the combined system together, when we put them in a box and just look at what this thing is doing, this equivalence is that I extract an amount of heat QC minus QC prime. The arrows has to be different. So essentially I will do it in the following way. I will write it down in QH minus QH prime or Q prime H and QC minus Q prime C. Right? The reason I have done it is in the following, because if the arrows were reversed, then it violates Clausius's theorem, statement of the second law. So it follows that QH minus QA prime H must be positive. If QH, that means QH is greater than Q prime H. Right? So it follows, since I am multiplying this, the work done is same in both cases. If I define, right, therefore eta Karnaugh, which is essentially W by QH, must be greater than eta non-Karnaugh. Remember, this is your proper Karnaugh engine, where you have taken the amount of heat Q prime H, and this is the one. This is the one which was your non-Karnaugh engine, which violates the Karnaugh's theorem. But it clearly tells you that if you were to design a non-Karnaugh engine where it violates the Karnaugh's theorem, then essentially you also violate Clausius's theorem. So question now remains is, what should be the efficiency? Eta, which is W over QH, which is 1 minus QC over QH. Now, for this case, we will consider two Karnaugh engines, one at T1 so operating the second one T2 and yet a third one which is at T3. So it takes an amount of heat Q1, dumps it to Q2, does an amount of work W12. This one takes an amount of work Q2, amount of heat, the same amount of heat Q2, and does an work W13 and dumps an amount of heat Q3. So this is what we call as Karnaugh engine 1, and this is what we call as Karnaugh engine 2. Once again, if I look at the combined effect of this engine, this combined effect of this engine is that I have one Karnaugh engine which is operating between the temperatures T1 and T3 and does an amount of work W13, right? This is so it extracts an amount of energy Q1, dumps an amount of heat Q3, correct? Now let's see. First of all, W13, this is wrong, this has to be W23. W13 is W12 plus W23. The total work that has been extracted from the two heat engines in tandem is equal to the two works W12 and W13. It also follows that Q1 plus W12 is equal to Q hot. So if I now apply the conservation of energy, then this means that Q1 is W12 plus Q2, right? But from the definition of this efficiency, I can write eta 12 as W12 divided by Q1. So therefore Q2 is Q1 1 minus eta 12, right? Let's look at, so this follows from the engine which works between T1 and T2. What happens for the second engine? So let's just briefly draw this again. Q1 CE1 does a work W12, Q2, the second one again takes a heat Q2, does a work Q3, sorry, does a work W13 and dumps a heat Q3. So this temperature is T3, this temperature is T2, this temperature is T1, and I saw that Q2 is Q1 1 minus eta of, we will write it down like this way. Similarly, for the engine which operates between T2 and T3, it follows that Q3 must be equal to Q2 1 minus eta T2 and T3. Right? So therefore Q3 is equal to Q1. If I just substitute for Q2 from the above equation, it's 1 minus eta T1 comma T2, 1 minus eta T2 comma T3. But now the combined engine does something like this. And Q3 is clearly Q1 times 1 minus eta T1 and T3. Equating these two equations, it follows that 1 minus eta T1 comma T2 times 1 minus eta T2 comma T3 must be equal to 1 minus eta T1 comma T3. Right? Now this equation is clearly satisfied if I have 1 minus eta T1 comma T2, which is equal to Ft2 for Ft1. So that there is a mutual cancellation on the left hand side, and what will be left out after the cancellation is only going to be a function of T1 and T3. And traditionally or conventionally, this is taken to be T2 over T1. So that the efficiency of two engines which operate between T1 and T2 is given by T2 over T1. This is how the Karnaugh efficiency looks. And you see, in this form expression for the efficiency, there is no material parameter involved over here. There is absolutely nothing that requires, let's say, like the specific heat of the system enters in this equation, or the compressibility or the susceptibility enters in this equation. There is no material parameter. The efficiency only depends on the temperature of the two reservoirs. So powerful is the Karnaugh theory. But remember, the point is that the Karnaugh engine is an idealized engine, right? And it is the maximum efficiency possible for any engine that you design which operate between two temperatures T1 and T2, right? So if I now write down 1 minus eta T1 comma T2 as Q2 over Q1, and this we saw was T2 over T1. Interestingly, let's just look at this part of the equation. and recast it in the following way. Now, when you look at the Karnaugh engine, which operates by taking an amount of heat Q2, an amount of heat Q1 from the hot reservoir, dumps an amount of heat Q2 to the cold reservoir, does an work W12. The machine has now operated in a cycle so that this has come back to its initial state. Recall in the PV diagram what we had two isotherms like this way, along which heats were taken, and then two adiabates. So this goes like this, but it comes back to this initial state, so that if it has come back to its initial state, the change in internal energy is zero, because internal energy is a state function, right? So it has come back to its original state, therefore the change in the internal energy is zero. But if you just look at this equation, in this whole process, you can see I can again write down this equation as Q2 T2 minus Q1 T1 is equal to 0. But the left hand side is clearly d cut Q over T is equal to 0. Because if I am to perform this integral for this particular machine, if I am to apply this for this PV for the Karnaugh engine, you see heat, let's look at this integral. The heat has taken place only at constant temperature, so it only happens over here. Therefore, I will have Q2, I will have Q1 and the temperature is constant. But here heat has been dumped. Energy added to the system is positive, energy dumped from the system is negative, taken out is negative. So it has a negative sign, minus Q2 over T2 for this part of this. No, in this part there is no heat exchange. In these two branches there is no heat exchange, therefore it follows this is equal to 0. So this equation, or equivalently this equation that we had written down, is the result of this integral. Now amazingly, you see that this is clearly does not depend on the path, but rather it depends on the two endpoints, right? So therefore I can write down this equation equivalently as d of s equal to 0, where now ds is defined as d cut q over t, where s is clearly a state function. Why? Why is it a state function? Because just like the internal energy, this is a state function. Because just like the internal energy, the system has come back to its original point. This closed integral is 0. The change in this value is 0. This state function is what we call as entropy. Once we have defined the entropy, ds as d cut q over t, we can write down this as tds, and therefore our first law takes the form minus fi dxi sum over I. Remember, for a hydrostatic system, let's just take a very small example. For a hydrostatic system, my generalized coordinates were v and n, and my generalized forces were minus p and mu. And therefore, your first law takes the form du plus p dv minus mu dn. Right? Once you have this, of course, now the whole of thermodynamics is mostly done. Now it depends on how you apply it to the system. I can determine the response function, which is T del S del T at constant pressure. I can define the specific heat T del S. Well, let's just take one step back and rewrite this as d cut Q over dt at constant pressure, which is T del S del T at constant pressure, and this is T. Similarly, this becomes del S del T at constant pressure. So if If I now want to apply, pressure is being held constant, volume is being held constant, so we will keep N fixed also over here, and this is just del U del T, volume constant, right? Just it follows from the first law if you carefully take the derivative. This on the other hand is del U del T pressure constant, del U del T pressure constant plus P del V del T pressure constant, right? N has been held fixed, therefore this third term is 0. Right. So this concludes our discussion on the laws of thermodynamics.